I'm Anil Kumar. Let us further explore and move on with our skills to learn algebra. So, in this part of algebra, we are going to learn about what is LCM, what is GCF, how do we find lowest common multiple and the greatest common factor with different techniques. We are going to learn three techniques to find LCM and GCF. We'll then see all the divisibility rules, including, interestingly, the divisibility rule for 7. During this journey, we'll have many examples and practice questions. At the end, we'll give you an assignment followed by the test. Let's really explore what is a product. Well, when you multiply two things, you get a product. You have been dealing with products for a long time, right? Area of a rectangle. Does that remind you of something? Here we have something for you. Let's explore it. Find possible integer dimensions of a rectangle with area of 36 meters square. That's the question for you. How can you find different values which, when multiplied, will give you 36? That is what the area is, right? We have a rectangle here, and the rectangle, as you know, has length, let it be L, and has width, let it be W. When you multiply them, what do you get? You get area. And what we are given here is that this area is 36 meters square. What could be the length and the width? Okay, come on. Yes, that is right. 6 times 6 is 36. Could we have some other combinations? Yes, 2 times 18, and likewise there could be few more. How can we ensure that we get all of these combinations? Here is a neat way of doing it. We, we can actually make a table as shown here with one column for length, the other one for width. And what are we looking for? We are looking for an area of 36. So if I take 1 unit of length, what multiplied to 1 gives us 36? Simple. 1 times 36 is 36. So we get one combination, correct? Similarly, we could take length as 2. 2 times what is 36? This is what you're going to ask yourself. 2 times 18 is 36. How about 3? Well, 3 times 12 is 36. Perfect. Does it go by 4 also? 4 times 9? Yes, 4 times 9 is 36. And you got it. 6 times 6, 36. Since now we have the same numbers, 6 times 6, going further will give us the numbers which are for the width. Well, I wrote length and most of my lengths are smaller than width. Well, these are just the variables associated with two sides. Even if you interchange them, it doesn't really matter much, right? So our widths are longer in this particular case. However, we got some numbers which when multiplied give us the required area of 36, right? That brings us to a very important note, and that is that when you multiply two numbers, what do you get? You get a product. So in this case, for example, we have 2 times 18 and that gives you the number 36. Clearly, these two numbers are not the only numbers. There are many more. And in this particular case, the combinations are 1, 2, 3, 4, and 5. And how many numbers in all? The total numbers are uh, not 10 because 6 and 6 is common, 9 of them. So what we say that these numbers which when multiplied give you the product of 36. So 36 is called the product. Yes, you know that. And these two numbers which we are talking about are called factors. So these are factors of 36, correct? And in this case, we can actually count them 1, 2, 3, 4, 5, 6, 7, 8, and 1, 9. And we have 9 factors of 36. You get the idea, right? So that is how we could do it. Well, this was a small number. We could easily do and find all the factors. We'll see now the techniques. How do we find factors of bigger numbers, right? And there is a real life application to it, as you can see. Area of a rectangle. How does that help? Good question, good question. How does this area of a rectangle really helps? Okay, let's explore that part. Or will you like to take that as a project? Well, this one. Let's explore it and let us see what we can do with length and width. We can also find the perimeter, correct? Yes, sum of all the four sides. So we know now that the combinations could be here, in this case, 5 of them. So we can put these values around the rectangle, add them up to find the perimeter, right? So now we are looking into the perimeter P, which is actually length plus width plus length plus width. Basically, twice the length plus twice the width, right? This is what we're trying to figure out. Okay, let's do our math. We can do twice L, which is, in this case, the first case, is 1 times 2 is 2, and twice 36, double it, it is 72. 72 plus 1 is 74. So we get this. Well, there could be alternate way. You could actually add first length and width and then multiply by 2, right? You could do like this. And that is the formula for perimeter. So in this way, you can derive new formulae, correct? Well, we did discover this, and keep on adding these numbers and then multiplying by 2. That is simpler. You multiply them only once. That is how it is simpler. So 2 plus 18 is 20 times 2 is 40, right? And we have 3, 12, 15. That gives us 30. 4 plus 9 is 13. Double it, 26. 6 plus 6, 12. Double it, we get 24. What do you notice? Well, the perimeter is very different. It has a range from 24 to 74. Well, does that help us in some way? Definitely. Perimeter normally means material cost to make something rectangular. For example, we could have a fence round it, right? We could have a fence around it, and this fence is going to cost us money. For the same area, smaller the perimeter, lesser cost, economical, correct? So these factors really help us. And you also notice that 6 by 6 is a square. Do you see that? So we learned a very important thing from here, that if we have a square, in that case, we have minimum perimeter for the same area. Do you see that? This is extremely important, and we are going to use this strategy in the following lessons, right? So now what did we learn? If we have a fixed area, right? So if we have let me write down first, right? For fixed area. So that means area is the capacity which you need, right? For example, if you are doing gardening, in that case, you want to have a maximum area for minimum cost of fencing. Correct, you got it. And that is the key to it. So you see, we have direct application of looking into the factors of the numbers. These numbers are not just the numbers, they represent real life situations and help us taking decisions, right? You got it. So let's move forward. We have understood what are products and what are factors. So let me just review this with some definitions, correct? So I'd like you to actually read what is there on the screen and make a note. Perfect. So now, what are factors? Well, factor of a natural number divides that number without a remainder. What does that mean? Well, we had 36. The factors were like 6 was a factor. If I divide by 6, what do I get? I get a zero remainder, correct? I could also divide 36 by other factors. For example, I could divide it by 18. 18 times 2, we know that was one pair. It gives you 36 also. 18 times 2 is 36. So in case of 36, all the 9 factors, when they divide into 36, the remainder is 0. That is what we mean. So I think we have understood this. Factor of a natural number divides that number without a remainder. Now, we took natural number here. Why natural numbers? Well, important. We are looking into whole numbers, right, as our factors. Product with these. No decimal numbers, correct? Because once you get those decimal numbers, it is not dividing into the number perfectly, correct? Right, this is important. Many times we may have to convert sometimes our decimal numbers to natural numbers and then work out with the division part. Why am I saying natural numbers? Well, you have to divide by something which is not zero, right? You could, therefore, that is very important. You could use another type of number here. Can anybody tell us? We learned about the number system, right? We can say non-negative integers, right? So we can say non-negative integers. Perfect. Non-negative integers, they are written by the letter z with plus. So non-negative integers is another thing which could be there in this definition of factors. So we now know that factors of non-negative integers divide that number without a remainder. Does it make sense to you? So we got this one. Perfect. Now let's talk about the multiple. Multiple of a number is product of that number with any other number, right? So multiple means like something like this. If I have 6, then 6 times 1 is 6, correct? What is 6 times 2? 6 times 2 is 12, 3 is 18. Likewise, all these are multiples. You remember your times tables? So whatever you get is the multiple. You will notice that all multiples of 6 are not the factors of 36, right? That is important to understand once again. So, as we move along and explore, there are many other things which you can learn from what you see. You observe, you get the idea. That is how these creative minds work. Okay, now let's talk about prime numbers. What are prime numbers? It may be a new term sometimes, right? Prime numbers have exactly two factors, one and number itself. So prime number is a special number which has only two factors. For 36, we had 9 factors, correct? Now, can you tell me some numbers which have only two factors? Well, you have many, right? For example, you know the number 11. 1 times 11 is 11, 13, 17, 19, and so on. There are so many other numbers which are prime numbers. An important thing here is that they have only two factors, 1 and the number itself. Now, coming back to this, what is the smallest prime number? Well, is it 1? No, I don't think so. 1 is it prime? 1 is not a prime number. So let us remember this part. 1 is not a prime number. Now, can anybody tell me why 1 is not a prime number? Because 1, how do you get? 1 times 1 is 1, right? So it is only one factor. It has only 1 as its factor. Remember, for prime numbers, we want exactly two factors. And therefore, 1 is not a prime number, right? So remember this. And you can see it clearly. Then, what is the lowest prime number? Coming back to it, could it be 2? Yes, it is. So 2 is definitely the lowest because 1 is the natural number, which is the lowest, and the next one is 2. 1 is not a prime number, 2. Now 2 has only two factors number 1 and 2, when you multiply them, what do you get? You get 2, right? So likewise, you can have many prime numbers. The simple test is that it should be divisible only by 1 and the number itself. And that is important, right? For example, 2, 3, 5, 7, right? These are single digit prime numbers, correct? You could write them here, 2, 3, 5, 7. Well, that is our list up to 19. Why don't you go up to the last number? So let's go up to 3-digit number, right? Or you can say maximum 2-digit prime number, right? Which happens to be 97, correct? So what I'd like you to do at this stage is write down all the prime numbers less than 100, right? Let this be an exercise. So we'll take 5 minutes and then see how can we write all prime numbers. Okay, let's continue with the lesson now. In the short break, you can actually make your list of prime numbers. Okay, if we know about prime numbers which have only two factors, if we have more than two factors, then what? Well, these are called the composite numbers, right? So now we have composite numbers which have more than two factors. Key is they have more than two factors, correct? So these are two keywords. Oh, exactly two factors are prime numbers and more than two factors are composite numbers, correct? Here we have another example. We are multiplying the two numbers 6 and 4. And what do we get? We get their product, which is 24. We also call this as a multiple, and 6 and 4 are the factors of 24. Correct? So we can say that 6 is a factor of 24, 4 is a factor of 24, 24 is a multiple of 6, 24 is a multiple of 4 also. Correct? Right. 24 is also multiple of 6 and 4, both of them. So these are different ways of interpreting our statement, which we'll call this as a multiplication statement, right? So this statement is also called multiplication statement or equation, right? Right. So I think everything is clear so far. You know exactly what are factors, what are multiples. You can also count the number of factors. You know what prime numbers are? Numbers with only two factors, and composite numbers more than one factor, and one, the number one, is neither one of them. Right. Now, let us see how do we work and use this information about factors in algebra. Correct. So here is an example for you. The example is list all the factors of 12 and 18. Write common factors of 12 and 18. What is the greatest common factor? Greatest common factor, GCF of 12 and 18. That is the exercise. Okay, so now you can take a moment and write down all the factors of the number 12 and then of number 18. So let's begin with 12. So as you know, 1 and the number itself, they are always the factor. So without thinking much, write at least these two numbers and then move on. We know 12 is an even number, so 2 will divide evenly in 12. 2 times 6 is 12, and then we know 3 times 4 is 12. How about 6? Next number is 6, which is already included. So once you go past your number, then you know they are going to repeat. So the 6 times 2 is already there. So we'll stop the list here. We get 1, 2, 3, 4, 5, 6 factors of 12. Similarly, let us write down the factors of 18. Well, number itself, when multiplied with 1, gives you the product of that number, which is 18 in this case. It is also an even number, so 2 times 9 will work, and then 3 goes in with 6. How about the other numbers? 4, 5, 6, 6. Okay, 6 we have already taken, and therefore we completed our list. It has 7 factors as listed here. So we've done the first part, that is to list all the factors. Is that clear to you, right? Now the second part says we need to figure out what are the common factors. Well, just match the list. What is common? 1 is common, 2 is common, 3 is common, and then 6 is common to us, correct? So from here, we have listed all the factors which are common. And the third part, which is C, is to figure out what is the greatest common factor. We're going to use GCF for greatest common factor. Greatest common factor, of course, is 6. And from the list, we can easily see that it is number 6. Simple process, correct? Yes, this is a very useful information. We'll have many application questions and see how greatest common factor helps us in many different ways, right? Like, for example, if you have 18 marbles and your friend has 12 marbles, in that case, we can make some shapes with your marbles combination, and the greatest common factor of 6 can help us out, right? So explore some examples where greatest common factor could really help you out. Okay, so it makes sense to you? Perfect. Here is what we have written for your convenience, the solution. So we just saw that for 12, these are the factors: 1, 2, 3, 4, 6, 12. And for 18, the factors are 1, 2, 3, 6, 9, 18. The way to write them was, first you write 1 and 12, 1 and the number itself, and then you move on. And when you move on like this, you see 2 and 6, 3 and 4, and then it comes to 6, which is already there. So coming back to 6 is already there. So if you do like this, you ensure that all the factors are considered. So this forms like a rainbow. Do you see that? So we have a rainbow here. So that ensures all factors are considered, right? So this is also important technique. So once you are writing, connect them. You know what multiplied with what is giving you the product in which you are interested. You get the idea, right? Then we've listed the common factors and shown what is the greatest common factor, which was 6. So I hope this exercise, whatever we have done, is absolutely clear. Can we move on from here? Yes, let's take more examples. Now this is an application question. Oh, as I was saying, we have many applications of factors. The question here is 30 square tiles of unit length are arranged in rectangular arrangements. So we come back to our rectangle, right? We got the numbers here, and the number here is 30. So we have 30 square tiles, right? So think like this. So we have these tiles, right? They're all square tiles. Correct. So like this, we have many tiles and total 30 of them. Now the question is, how many different arrangements can be made? And we are looking for what arrangements? Rectangular arrangements, right? And we'll assume that length of each and width of each tile is just 1 unit. So it becomes easy to calculate some numbers in which we may be interested, correct? For example, the cost of the tiles to cover a particular area. So that becomes the direct application. So this could lead us to an application which is what? Which is cost of tiles to cover an area, right? So then you can explore on this, knowing cost of one tile and 30 tiles, multiply them, you know the cost of tiles. But more important here is you can also figure out the maximum area, right? So the conclusion here will be what is the maximum area, right? So you know the cost is fixed, but to make the best use of it, you can cover the maximum area. What kind of arrangement should you make? That leads us to from where we started. So that is how everything is connected. Perfect. But let's figure out here how many different arrangements can be possible. Now, how do we figure this out? How many? That means we're looking for that rainbow, right? And in this case, the number is 30. So 1 times 30 will give us one arrangement. That means we have everything aligned in one row. So that is 1 times 30. Perfect. And then we can have 30 is even number. 2 times 15 could be the next combination. 30 is 3 times 10 as we know. 4, no, it doesn't go with, but 5 times 6 is the next number. So we have how many arrangements? Well, this is one arrangement. This is the second arrangement, third, and fourth. So in this case, we have 4 arrangements. Do you see that? 4 arrangements, correct. Now the question is, can a big square be one of the arrangements? Well, why are we interested in square? We found that square gives us maximum area, right? For the same perimeter. The other way. You get the idea? The other way. Okay. So now the question is very important. Can a big square be one of the arrangements? Well, we are working with 30, 30, not 36, correct? We are working with 30. Now, 30 is not a perfect square, right? So, therefore, we cannot make. So, this is not a perfect square. So, your rectangle will not be a square, right? So, the sides, length and width will be different using these 30 tiles, all of them together. You get the idea, right? So not a perfect square, and therefore the answer here is no. So you have to look into the product. If it is a perfect square, only then you can form an area, rectangular area, which is square in shape. Perfect. Otherwise, what you get is a rectangle. So that also is kind of a definition for square, right? Okay, so this is very important. I hope you appreciate it. So let's explore further. Now, we'll now look into bigger numbers. So, like numbers like more than 100. Okay, so here is the next question for you. I'd like you to just copy this question and try to answer. Okay, the question here is again related to greatest common factor, but we have three numbers now. Okay, it says find the greatest common factor GCF of 30, 72, and 120. Right. So we have three numbers. What we know is that we'll make a table with these three numbers 30, 72, and 120 and list all the factors. So that is what we are going to do. And that is what I've shown here. Later, you can do it on yourself. Strategy remains the same. We're going to make a rainbow. 1 and 30, we know. 2 and 15, 3 and 10, 5 and 6. We just saw this number, but now we have bigger numbers, 72 and 120. Follow the same process and list all the factors as has been listed in this particular table. So we have done first part, which is to know what the factors are. The second is to figure out the common factors. And we're looking for the greatest common factor, correct? So now let's find the greatest common factor. So GCF is the greatest common factor. Begin with the smaller list. So do we have 30 in all others? No. 30 is only in these two, but it does not exist for 72. How about 15? Well, 15 is there in the list for 30 and 120, but not for 72. How about 10? 10 is also there in 30 and 120, but not in 72. How about 6? Well, 6 is common to all. You see that? And therefore, we get a result, and that is 6 is the greatest common factor. So we can now write down that the greatest common factor of the numbers 30, 72, and 120 is 6. Is that clear to you? But you can see there was a lot of work to be done here. It takes a whole lot of time to write factors of big numbers. Sometimes we may miss some factors, so there is scope of error. You get the idea? If I would have missed 6 from any one of them, then what happens? I get a wrong answer after doing so much of work. It's not so good. So we should have some way of doing it and ensuring that it is always right all the time. Doesn't matter how big the number is. Well, for that, we have a very beautiful method. It follows Euclid's algorithm. Well, scary name for you, the young childrens? Okay, but anyway, you are bright minds and you can easily see how this algorithm is going to help us find the greatest common factor, right? Do you know how to divide numbers? That is what we are going to do. And we'll learn this Euclid's algorithm. So that is what is something very important. So we will see how by division we can find the greatest common factor rather than multiplication or factors. Do you see that's a twist to our strategy? But an interesting one. Are you all excited about it? Right? Okay. So again, the same question, which is how do we find the greatest common factor of 30, 72, and 120? Okay, so the strategy here is begin with the two big numbers. You can begin with any two numbers, right? So what I did here is in the example, I started with 72 and 120, but well, you could start with 30 and 72 also. Not a bad idea. Okay, but we'll prefer to begin with the big numbers. Divide the larger number with the smaller one. That is what we could do. We could not do otherwise, right? We're working with natural numbers, correct. So here, what I've done here is that I'm dividing, you see the division? So this is the division, and I'm dividing 120 by 72. 1 times 72 is 72, and when you take away 72 from 120, you get 48. Correct. Now, clearly, 72 is not a factor of 120. So, this division shows that when you have a remainder, then that number is not a factor. Correct? Now, if 72 is not the factor, what is the other number to try? The difference of these two numbers. Do you see this difference of these numbers, right? So, let me write here difference of these numbers. So the difference of these numbers is 48. So what we are going to do here is that we are going to replace 120 with 48. And we are now going to divide 72 by 48. Do you see how we switched? We now made 72 to be divided by 48. So the divisor changed, right? So divisor is switched, right? You see, divisor is now the remainder. Or I should say remainder is now the divisor, right? So I should say remainder is now the divisor. So the remainder 42 is the divisor. And the bigger number is replaced by the earlier divisor. And the bigger number, I should say larger number, right? Okay. Larger number replaced by earlier divisor. So this is continued. So that is the strategy. So what we did is the remainder of 42 now becomes the divisor, and the earlier divisor 72 is now being divided. Dividend. So that becomes the dividend. So these are the three terms which are normally used in division, right? So let me just summarize them. So if you are dividing, right, so what do you get here? So if you do that, there is some number here and some remainder here. So R is the remainder, and this is your divisor. Okay, this is your quotient, and that is your dividend. Let me write it full. Clear. So what we are going to do is switch the numbers as shown here. So now you divide by 48, and 48 goes one time. 48, when you take away, leaves us with 24. 24 now becomes the divisor, and 48 is your new dividend. When you divide it two times, you get exactly 48 remainder is 0. That means what? That means 24 is the greatest common factor between the two big numbers 72 and 120. You get the idea. Check it out. So what we got here is the number 24, which divides evenly into whatever we had. And what we had was kind of difference of the earlier two numbers. Many times we found the difference, correct? Important thing here is that the greatest common factor remains same even between the difference of those numbers, and that is what the Euclidean algorithm is, correct? So first let's see the process. We found that 24 is GCF of 72 and 120, right? Since the remainder now is 0. You see, we did not even factor. So we have found the greatest common factor without factoring. Interesting. Well, let's check with the third number, which is 30. So we have our key number 24. Divide 30 by 24. Well, it doesn't go. 1 time is 24. Remainder being 6. Now switch the dividend. It becomes 24. Divide 24 by 6. And what do we go? What we get here is again a remainder of 0. And the number which really does the trick for us is 6. So therefore, the GCF is 6 for all the three numbers. So even while working with large numbers, we could easily find the greatest common factor in few steps without factoring them or without listing all their factors. So that means we have avoided a mistake which can happen when you list all the factors, and we have also cut down on the time. So this is amazing, isn't it? I hope you loved it, right? So 6 is the greatest common factor of 30, 72, and 120, correct? You can check yourself. All these numbers, 30, 72, and 120, are multiples of 6, right? And that is, when you list it out, will be the greatest number, which will be the factor of these, correct? Now, from here, we have learned a very important strategy. Now, this strategy, in the name of the great scientist, mathematician, who is called algorithm of Euclid's or Euclidean algorithm, right? It is based on the fact that the greatest common factor of two numbers does not change if larger number is replaced by the difference with the smaller number. So the larger number, which was 120, was replaced by the difference 48 in this case. You see that? That is what it is. Extremely important. When I was learning this, I could never get it. But now I understand, and I hope you also understand. So, this kind of a very special division helps us to find the greatest common factor without even listing all the factors. It really helps when we are working with many numbers and large numbers, right? Okay, now let's see. Another example with some other values. So this is for you. It's a practice question. So the practice question for you is find the GCF of three large numbers, and these large numbers are 54, 108, and 144. And this time you have to use two different methods. So when I say two different methods, one you have learned is to list all the factors, right? So method number one was list all factors, correct? And what was the second method? Second method was a special division. And what strategy did we follow in special division? It was Euclidean's algorithm. That is the strategy. Euclidean algorithm is based on the fact that the greatest common factor of two numbers does not change if the larger number is replaced by the difference with the smaller number, right? So that is how it is done. Okay, so I like you to take some time and do this division and figure it out, correct? So the idea here is you can take the two numbers, which is like 144, and divide this by 108, right? and 108 goes one time, you get 108. Find the difference, and this time difference will be what? It is borrow from here 14, so it is 6, 3 left, 36, and divide 108 by 36. So replace, do you see what we have done? We have replaced the bigger number by the difference. So this number has been replaced by the difference. Correct? So now in our list, we're trying to figure out what is the greatest common factor between the numbers 54, right? We replaced 144 with 36, right? 108 and 36. Think like this. So we have actually cut down on the numbers which we are working with. You see this? And that is a beautiful trick. And well, this goes 3 times. 6 is 18, and this is 108. So that gives you a zero remainder. So that is the first part. We got 36 as a key number. Now try 36 with the other number, which is 54. So one time will give us what? Take away 36, and it is 6. When you take away from 14 is number 8. And when you take away from 4, 1, you get 1. So we have 18 here. Divide 36 now by 18, 2 times is 36, leaving the remainder 0. So that gives us the greatest common factor. What is the greatest common factor for these numbers? Well, it is 18. Do you see? Even without listing all the factors for such big numbers, we found the greatest common factor. Isn't that amazing? Yeah. So the huge applause from you shows that clearly you all appreciate this method. What you need to do is practice. Take up any 3 numbers and then practice. Perfect? If the numbers are small, you can still do, right? With this method, it is very simple. Okay, so now let's move on and take more examples. This becomes a practice review questions for you. You have learned today till now what are factors, what are multiples, how do we find the greatest common factors. Now, based on this, here are 7 questions for you. I'd like you to take a moment and answer these questions now. Let's go through them one by one. The very first one is simple. True or false? So the true or false question is, all natural numbers are either prime numbers or composite numbers. What do you say? All natural numbers are either prime numbers or composite numbers. What do you say? Yes or no? Why not? Correct. There is a number 1 which is neither prime nor composite. So this statement is false. You are right. The next one is all prime numbers are odd numbers since the even numbers are divisible by 2. Well, we have a prime number 2, correct? And therefore, this statement is also false. 2 is an even number, which is a prime number. Correct. So we have understood that the lowest prime number is 2, which is an even number. So 2 is actually the only even number, right? So the only even number. That is correct. Question number 3 for you is, what is the greatest common factor between two prime numbers? Between two prime numbers, do they have a common factor? Interesting. 1 times the number itself. 1 times the number itself. Well, it is number 1. Correct. So that is how you get this answer. Question number 4 for you. Can you please read the question and then answer? Well, let's read it. It says, what is the greatest common factor between a number and its multiple? So the number and the multiple, we are looking for the greatest common to both. It is the number itself. Right. So it is the number itself. So we get this answer, the number itself. For example, if I take the number 7 and 21, so in this case, what is the GCF? Well, the GCF is 7, correct? 7 is common to both. So the GCF here is 7. So we have understood this part. Critical question. Next, question number 5. Can you please read and answer? Find the greatest common factor between 16 and 24. So you could adopt any of the two methods, right? What do you get? Did anybody get this answer? Well, let's do quickly. We could divide 24 by 16. That was easy, right? And when you do that, you get 8, which goes evenly in 16. And therefore, the answer is 8 for us. So without listing the factors, we got our answer. Do you see how fast it was? Amazing method. So we'll call this as a special division for finding the greatest common factor. And this is indeed the most effective method for you. So the next two questions, I will leave it for you. And this becomes your assignment. Is that clear to you? So this becomes your assignment. You need to now find the greatest common factor of the number 112, 140, and 196. So this is your assignment, okay? And that one also is your assignment. Can you please read this? Now, if you have doubts about it, how to do it, you can ask me now, right? The question number 7 here is, rectangle with area of 108 meters square has perimeter of 62 meters. Find its length and width, right? So you can figure out the length and width when you know both area and perimeter. Interesting. We did not take this type of question, so think about it. So the whole idea here is to think and get the answer. Is that clear to you? And when you are finding the answer, use the most efficient method. So that is what the critical thinking is, which we have been talking all along. Correct. So I hope you are enjoying this journey of learning with me, right? Now let's move on and see about the multiples now. So we have seen the factors. Now let's talk about the multiples. The example here is example 3, where we'll see the multiples. The question here is, list first 5 multiples of 6 and 4, not the factors, multiples. Right? So what will you do? You write 6 and 4 and write down their multiples. So first 5 multiples means really 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, right? Which is 30. So likewise, list all the multiples for 4 also. Okay, 4 times 1, and then we have 8, and then we have 12, and then we have 16 and 20. So we have done the first part, that is to list first 5 multiples of 6 and 4. Now the next question is, what is the lowest common multiple? So we are now interested in the lowest common. So let's kind of circle what are common. Okay, between 6 and 4 we find 12 as common. And in this case, since we only listed 5 multiples, we have common factor of 12. So the lowest common, that is for sure, is 12 only. So the lowest common factor between 6 and 4 is 12. That is how we can find it. Correct. Now, the question is, what multiple of 6 and 4 is closest to 1000? So that becomes the lowest common. And we are now looking into what multiple is closest to 1000. So how do we do that part? So I'd like you to take a moment to think about it. Closest to 1000, right? So how will you do this part? Which is closest to 1000? We know 12 is the lowest, and now the other factors will be what? Well, other factors will be multiples of 12. So 12 and then 24 and then 36 and likewise. But we have to go somewhere close to 1000. You get the idea. This is what we're trying to figure out. Okay, apply different kinds of strategies. One could be, well, divide 1000 by 12 and you get some number here and some remainder there. We don't want remainder. You get the idea. We don't want remainder. So reduce the number by the remainder. You will get your number, right? See whether it is closest to 1000 or not. So that is how you could think about it. Correct? So the idea is to think. Right. So think about it. Okay. So I think you got this solution, right? How are you thinking? Yes, can you explain me your strategy? Well, you got a number here, you get, well, how do we divide this? It goes 8 times is 8 times 2 is 96, and you get a remainder of 4, 0, and that goes 3 times. So 83 is perfect. And so what you did was that you did 12 times 83 to get your answer. Is that clear to you? Right? That was your strategy? That is correct. And 12 times 83, you could do 10 times and then 2 times and add them up to get the right number. Do you see that? So you could do this. Or you could use other strategies of multiplication. Correct. So there are many different ways of multiplying, or you could straight away multiply 83 by 12. First by 2. You get 2 times 3 is 6, and then this is 16, and then add 83 to it. Perfect. And what you get here is 699. 996 is the number you get. So that becomes closest, which is also the multiple for the two numbers 6 and 4. That could be one strategy. Can you think about some other strategy? Well, we know 1000 is a multiple of 4, but 1000 is not a multiple of 6. Does that help? Well, now since we know the answer, how does that help? That 1000 is a multiple of 4 but not of 6. Let's look into our solution. Well, in the solution, what we have done is we have listed all the multiples of 6 and 4 as we did, and we found that 12 was the lowest common multiple. That is perfect. Now the question was, how do we get a number closest to 1000? We found one strategy. Now here is a very cool method of doing it. So we have 1000 and we know that goes by 4. Perfect. But not by 6, right? So as far as 6 is concerned, it is not a multiple of 6. So what we do here is that since it is not a multiple of 6, we can try the two numbers which are above or below. Well, the number above is, if you add 4, you get 1004, and the number below will be you take away 4, which is 996. And what you notice here, that 996 is also divisible by 6. Well, we'll learn divisibility rules to understand it better, right? Or faster we can do this calculation. So divisibility rules of 3 and 2. So it is an even number, and when you add it, it can be divided by 3 also. So it is divisible by 6. So this is a faster technique. No division required. Do you see that? That is what we talk about critical thinking. So the critical thinking here was, we're looking at the number 1000. Do you see that? We're looking at the number 1000, and 1000 goes by 4. We know it, correct? Last two digits you check, 00 goes with 4. We'll learn this rule in today's lesson. Okay, but it is not a multiple of 6, since 6 needs 3 also, right? And you cannot divide this number by 3, simple as that. So what we did was, we know the multiples of 4 closest to 1000 are 1004 and 996, out of which 996 works for us, and that becomes the solution. Is that clear to you? That is how we have done. So we looked into the multiples of 4 which are closest to 1000. And then from here we figured out that 996 is divisible, and therefore that becomes our solution. Do you like this approach? So no need of that big division, right? Division is sometimes very difficult. Okay, so now we are into the application set. Now here is a question for you, which is, there are 6 bags with equal number of marbles. Sam counts and then mixes them all in one bag to distribute equally in the other 5. He finds that the number of marbles in each bag is now 3 more than what it was earlier in the 6 bags. How many marbles were there in all? I'd like you to again read this question, right? Till then, let me just do some thinking. So what we have here is, we had 6 bags, right? So we had 6 bags, 1, 2, 3, 4, 5, 6. And all of them had equal number of marbles, right? So let's say they all had some equal number of marbles. Let me say X marbles, correct? X, some marbles. We don't know how many. So whenever we don't know how many, we just write a variable, right? And what was done to this? They were all mixed up and replaced into 5 bags. 1, 2, 3, 4, and 5. Correct. And in these 5 bags, because the bags are only 5, not 6, more marbles can be there in each bag. Okay. And how much more? They say 3 more. Okay. So x plus 3, x plus 3. That is what the situation is. But what is important here is that the number of marbles is fixed, right? Number of marbles is common. Do you see that? So number of marbles is common. So what are we looking at? Since the number of marbles is common, we are looking at the lowest common multiple of x and x plus 3 or 6 and 5. What are we looking for? Okay, think about it. Think about it. So how many marbles were there in all? That is the question. Correct. You are right. So what you get here is that we have two numbers which are 6 and 5. We're basically looking at the common factor. Well, the common factor, no, the common multiple, right? So, okay, lowest common multiple. So lowest common multiple is 30. So the number 30 is common to both. If you list all the multiples, 30 will be common. If I have 30, in that case, in these bags, how many will be in each? Well, 6 times 5. Then in that case, there will be, let me write in a different ink, 5 in the bag, 6 bags, and 6 each in the other bag. You get the idea. So that is how we relate everything which we have learned. But now the difference is how much? So now the difference is, let me write down difference like this, right? So difference is equal to only 1. But what do we need? We want a difference of 3. We want not 1. So 3. That means we'll multiply this number by 3 to get our answer. And the answer now is 90. You get the idea? So if we have 90 marbles, then they can be distributed in 6 bags and also in 5 bags. Let's figure out. If I distribute 90 in 6 bags, what do you get? So dividing 90 into 6 equally will lead to what? 6 times 1 is 6, and then we are left with 30, which is 5. So we will then get, let me write down there, 15 marbles in each. So the value of x now is 15. Now, let's divide 90 also by the number 5. So if I divide 90 by 5, so 5 times 1 is 5, we get 40, and that is 8. So we get the number 18 here. Clearly, the difference between the two is 3. So we have plus 3 for the marbles in 5 bags. So you see how important this question was. It's a very difficult question, and you can see this question in many competitive exams. So learning with us will also prepare you for competitive exams like Olympiad, right? Or Math Kangaroo, or many others. That's interesting. So these concepts are really going to help you in coming times. Okay, so let's look into this question in a different way, and that is again the same question, right? But anyway, we now know the solution. So the solution here is that in 6 bags and in 5 bags, we could have common multiples. And these common multiples could be 30, 60, 90, 120, and so on. Correct? Lowest is 30. But what do we want? We wanted how many bags are there when 3 more are in 5 bags. So in case of 30, there was only 1 more. In case of 60, 2 more. In case of 90, 3 more. So that becomes the solution for us. So that is how we can visualize our solution. Is that clear to you? So it's important that while we are learning, we should record our learnings so that they can be recalled very easily later on. Correct? So that brings us to an end of a very important topic. We have learned about greatest common factor and the lowest common multiple. So here is a practice set for you. Take it like a test, right? So, okay. So these 5 questions are there for you. I'd like you to pause the video, copy these questions, answer, right? And then we'll move on with suggestions. Correct. Okay, so let's look into your suggestions on question number 1. The question here is, what is the largest 4-digit multiple of 6? Largest 4-digit multiple of 6, correct? So 4-digit multiple of 6. You're looking at multiples of 6. So how will you do it? Think about it, right? So that's strategic thinking for you. And the second one here is, the LCM of 4 and 6 is 12, correct? You know it. So LCM of 4 and 6 is 12. That is given to you. What is the largest 3-digit multiple of 4 and 6? So this time we want the largest 3-digit multiple of 4 and 6, right? Another very interesting question. So basically, we have given you the LCM for 6 and 4, which is 12. So we know this is a multiple of 12, correct? So you're looking for a multiple of 12, which is closest to 999. That is your largest 3-digit number. You get the idea? So that's the question. Now, the question number 3 is, what is the largest 3-digit number that will leave remainder of 3 when divided by 4 or 6? So this time, remainder is required 3, and you're looking for the largest 3-digit number. So again, is the largest 3-digit number. However, that is not the multiple, right? It is 3 more than the multiple. So very tricky question, correct? Think about it and answer. Next question here is, what is the least common multiple of a number and its factor? Number and its factor, least common multiple. What do you think it is? Okay, that's right. And question number 5 is, what is the LCM of 1 and any other number greater than 1? Straightforward. So I think you can get most of it. So with that, I'll leave this as an test for you, right? So I'd like you to take this as a test and submit your answer at the earliest. Perfect. Let's move on and see how do we do this part of lowest common multiple in a faster way. For greatest common factor, we had this special Euclidean division. Now, how do we do LCM? Because LCM involves multiplication of numbers, so we are always working with very big numbers. So here also we have a very special division. This question and the method will help you understand. So the question is, we are now looking for LCM of 3 numbers, right? Just as we did for 3 big numbers, right? The Gcf. Okay, the question is, find the least common multiple, LCM, of 14, 20, and 35. Now this method is called a ladder division method. So we are going to take 3 numbers together, divide them, and take out the common factors. So the idea here is to take out the common factors, and that's what is written here for you. Ladder division is based on the fact that the common factors between 2 or more numbers can be taken out by each division, right? And that's how we'll do it. So let's see how, correct? So, for example, let me first give you a simple example. If we are talking about numbers 6 and 4, then if you multiply them, what do you get? 6 times 4 is 24. Well, 24 is a multiple of 6, but not the LCM, right? So to get to LCM, what do? We take away common factor. 6 is 2 times 3, right? And 4 is 2 times 2. As you can see here, 2 is common to both. It is being multiplied by itself twice. We are looking into only one factor. So what we'll do is that we'll take away one of them and then we get our answer. Taking away one of them is as good as dividing 24 by 2 and then 12. 12 is also a factor, a common multiple of 6 and 4, a factor of 24. So that becomes now the lowest common factor. So the process was to divide by 2 and then we get our answer. Do you see that? Okay, so with two numbers we did. Now here is an example with three numbers. So let's follow this example. So here what I'm doing is we have taken two numbers which are 14, 20 and 35 and we're going to divide these two numbers by whatever is a common factor of these. Since 14 and 20 are even numbers, we can start with 2. So we'll divide both these numbers by 2. We get what? 7 and 10. 2 times 7 is 14, 2 times 10 is 20. 35 cannot be divided, so write it as such. Do you see that? It cannot be divided, write it as such. The idea is, even if you get common factors from two of them, you are reducing the multiple, right, by that factor. This is important. So we start with the biggest or the largest or the big number, and then we reduce it to the smaller number. How do you get the big number? The big number is by multiplying all of them and then keep on reducing by division. That is the process. Now what do you notice here? You notice that 10 and 35 can be divided by 5. So divide this whole thing by 5. 5 goes 2 times with 10 and 7 times with 35. As far as 7 is concerned, it cannot be divided, does not have a factor of 5, so just copy it as such. So we now have two 7s which can be divided by 7 further. So that gives us 1, 1 for the two 7s since one of the 7 has been taken as a common factor. So you see how we are reducing these numbers and ultimately we are left with some numbers which are 2, 5, 7 and 2. When you multiply these numbers, you get your answer. So these numbers when multiplied, they have nothing in common, right? They when multiplied will give you the lowest common multiple. Do you see this process? Isn't that amazing? So you don't have to write all the multiples and check which one is the lowest common multiple, correct? So that is another amazing method to do. And I hope with this you can now do questions related to lowest common multiple. It has huge application, right? You know about it, adding fractions, right? The rational numbers. We need the lowest common denominator, and that denominator comes from the lowest common multiple. Is that clear to you, right? So that is how we can actually do it. Now let's look into the next part of it, which is again an assignment for you. And in this particular assignment, we would like you to take these questions home, answer, and submit them online. You can send as an attachment to my email address given here, right? So I'll check that and get back to you. For any questions for that matter, get back to us and we are going to always address them and explain you how do we find a solution or how do we clear the point or how do we move forward from here. That is the most important part of our learning. Perfect. So these four questions for you. I'd like you to pause the video, copy them, and then take them as assignment. So this is an application assignment. Question number 1. I love collecting stamps. Today I have less than 1,000 stamps. These can be arranged evenly in 3, 4, 5 or 6 columns. Find the maximum possible number of stamps in my collection. Correct? So that becomes the first question clearly. When we say that these can be arranged in 3, 4, 5 or 6 columns, we are looking for common multiple closest to 1,000 but less than 1,000, right? So that should help you. Question number 2. In a temple, a bell rang every 4 minutes and lights flashed every 6 minutes. Both these events started at 12 noon. Find the times when both events coincide in the first hour. how many times will both events happen together till 1 p.m.? That is in the next hour. Correct? So that becomes your second question. Again, we're looking for the common multiples for 4 and 6. Time is in minutes. Hours, you remember, 1 hour is equal to 60 minutes. So that should help you to figure out the possible solution. Okay, question number 3. Length of a rope is between 2 meters and 2.5 meters. It can be cut exactly into 8 centimeter and 12 centimeter. Find possible lengths of the rope. Now, again, there is a switch of units. So we have 1 meter, which is equal to 100 centimeter. So use this conversion, convert all the numbers in 1 unit, and then try to look into the solution. So length of the rope is between 2 meters, could be considered as 200 centimeters, and 2.5 as 250 centimeters, correct? So you can say 200 centimeter to 250 centimeter, correct? And then can be cut exactly into 8 centimeter and 12. So those are the two numbers whose LCM is of your interest. So figure this out. Simple as that. The last question here is, 5 rectangles have exactly same area. A length of these rectangles are lengths of these lengths of these rectangles are 12, 14, 18, 21, and 24 respectively. Find the area, find the minimum value of area A. Okay, once again, question number 4 for you is, 5 rectangles have exactly same area. So we are looking into rectangles, think about them, right? Length of these rectangles are, it has a fixed area, right? So the length is different. So length is a variable. So lengths are 12, 14, 18, 21, and 24. Find the minimum value of A. So minimum value means lowest common multiple of these numbers. So that is how you can understand a question and see how our learnings help us answer so many different questions. Is that clear to you? So that is an assignment. You can actually take this assignment home, submit the solution, and then we'll discuss its solution in the next class. Perfect. So let's move on to the next topic, which is we'll talk about the prime numbers now. Okay. So what are prime numbers? We just know the prime numbers have only two factors, one and the number itself. So again, the definition for prime numbers is that prime numbers have exactly two factors, one and the number itself. And here is the list of prime numbers which we discovered earlier. So this is up to 19, less than 20. So these are the prime numbers which are less than 20. Composite numbers, as you know, have more than two factors like 4, 6, 8, and so on. So these have more than two factors. For example, the factors of 4. What are the factors of 4? It is 1, 2, 4, right? Factors of 6, 1, 2, 3, and 6. Factors of 8 are 1, 2, 4, and 8. We have seen them so many times in our earlier lesson, right? Now, what do you need to explore? That is kind of important. So now we are talking about prime numbers. Get ready with me. And how do we use these prime numbers in finding LCM and GCF? That is going to be our topic from now. So we know all about LCM, GCF, and also prime numbers. And how can we combine all this to solve effectively many questions, right? Right, that is what it is. So here what do we need to explore is explain why a composite number will always have at least one prime factor. Oh, composite number will have at least one prime factor. So this is important. What do you think? A composite number, let's see. We have 4 a composite number. 2 is a prime factor. Rest. Factors for 6, 2 is there. For 8, 2 was there. Oh, if I take number 9, then 3 is there, correct? Yeah, 3 is there. So yes, it makes sense. Why Simply because if it is not prime, it can be factored further. Correct. That is true. So that becomes your solution. Isn't it interesting, right? Now, is 1 a prime number? You know it, right? So answer, is 1 a prime number? How many factors it has? Part C is, how many prime numbers are less than 100? That's critical. How do I know it? How many prime numbers are less than 100? So you have to list all of them, right? List all and then count. Is that clear? How many? Okay. The last question here is, list all prime numbers less than 100. Well, that is also part of the question. So, well, I'll give you a hint. The answer is 25. So you should have 25 prime numbers. There are 25 prime numbers which are less than 100. So that will help you to check your list. So when you make your list of all the prime numbers less than 100, it should not be any other number but 25. Okay. But how do we ensure that we have written all the prime numbers correctly? Well, the key here is that composite numbers always have at least one prime factor. At least that means every number we have to see whether it can be divided by a prime number or not. That makes simple, correct? Okay, we're talking about 100. So, so numbers like 100 is like 10 times 10, right? So I think the prime numbers less than 10 should work for us. So yes, I think the idea is great. So we are now putting this idea in place to figure out exactly how many prime numbers are there less than 100. Oh, so I'm actually providing you with the solution right here. I'll tell you the strategy. So the strategy here is that we're talking about 100, correct? 100 is 10 times 10. Okay. So clearly we have to look for numbers which divide into 100 and less than 10. So can you tell me the prime number less than 10? Well, it is 7. So basically, we have to check all the prime numbers, which are 2, 3, 5, and 7. So if a number can be divided by 2, 3, 5, and 7, it becomes a composite number, right? So we have to divide our numbers again and again by 2, 3, 5, and 7. Those which are left are prime numbers. That is the concept. Okay, so let's begin. So what I've done here is, since we are dividing by 7, I made a very special table. This is not 10 by 10. This is like 6 by whatever. We'll go up to 100, right? So it should be continued till 100. So the idea I'm going to discuss here is, how do we find prime numbers from the list of numbers? We know 1 is not a prime number, so cross this out. 1 is neither prime nor composite, so cross this out. We know 2 is a prime number, 3 is a prime number, 4 is not a prime number, 5 is a prime number, 6 is not a prime number, right? So that was simple. Less than 10 is very simple. What else we know? We know that these numbers which are even cannot be prime, so we'll strike them out. So they are not prime. We can continue with this list up to 100 or even more, right? You can go up to 200. Okay. Now this column here, interestingly, has all the multiples of 3. Do you see the advantage of making this table up to 6? So clearly, these are all multiples of 3, so they are all gone. Right. How about 5? The multiples of 5. So check for multiples of 5. The multiples of 5 are in this particular diagonal. Do you see 5, 10, 15, 25? Okay. The next is 5, 30. So 30, 35, 60, 55. Okay. So likewise, we can actually go through this list, right? And then strike out all the numbers which are multiples of 5. So we know 5 is another prime number to work with. Now the most difficult prime number is 7. How do we get the multiples of 7? Well, 7 goes through another diagonal. Once we are at the end of such a table, we are going diagonally. So 7, 14, 21, 28, 35, 42. Okay, these are not the prime numbers. They are divisible by 7. The next number will be what? After 42, we are looking for what? As a multiple of 7. We are looking for 49, right? So this is how we'll go. further. So those are not the multiple of 7. So likewise, you see how we crisscross the whole list, right? And cancel out so many numbers. Well, clearly, we should have cancelled these 4s also. All the multiples of 4, these are all the multiples of 4 cancelled. No more with us, correct? Okay. Now, where are we? We're looking into even numbers, which are all multiples of 6. Okay, so they are all gone. So we are left with some numbers now on the screen. And these are your prime numbers. Does make sense to you? So the prime numbers are the numbers which are now left. Okay, because 7, we were cancelling those numbers with, is definitely a prime number. And so you can now list out all the numbers which have not been crossed out. So do you see how easy it was? We did not even have to divide to get our result, and we can extend this to any number, correct? Now, you see how beautiful it is? So now extend to 100 to get all your numbers. And remember, there are 25 prime numbers, so this will help you to, that count will help you to figure out that you've done the right thing or you have not missed anything out. Is that clear to you? Perfect. You love this. So this is the best way of listing all the prime numbers. Right. Now, why did we do all this? We were looking into LCM and GCF, right? Now let us see how does these prime numbers help us to find the LCM and the GCF. We call this process as a prime factorization. So we knew factoring, correct? Now prime factorization, well, that is unique way of writing all the factors of a composite number, because we have seen that composite numbers finally end up with division by the prime numbers. That's the whole thing, right? So, okay, so here is a definition for you. Prime factorization is representation of composite numbers as a product of its prime factors. You get the idea. So all the composite numbers can be divided by the prime numbers, and therefore their product will lead to the composite number. So both ways. Correct. Well, we'll take examples to really understand it. Okay. So why is it so important to do it? So when we are writing only the prime numbers as the factors, we have a unique set of numbers to work with. We'll see it soon. And how do we do it? Okay, let's take an example. So what I'm going to take here is the number 12. 12. You can divide 12 by 4 and 3. 4 times 3 is 12, right? Just take any two numbers. It's a composite numbers. When you multiply 4 and 3, you get 12. But you know 4 is 2 times 2. So replace 4 by 2 times 2. So now you can write 12 as 2 times 2 times 3. You get the idea. So we have 12 as prime factorized, where the only factors are the prime numbers 2, 2, and 3. There are two 2's, so I could write in the shorter form 2 squared with the exponent, right, times 3. And we get the prime factorization of 12. Do you see that? Or you could also, the 12 is 2 times 6. You could begin from there also, it doesn't matter. And 6 is 2 times 3, and therefore prime factorization of 12 is again 2 times 2 times 3. We came up with the same number. You get the idea. Correct? Let's try another number. For example, if I have 18. Now 18 we know is 2 times 9. 2 is a prime number, but 9 is a composite number. 9 could be written as 3 times 3. And now you will notice that 18 is basically equal to 2 times 3 times 3. So when we write this dot in between, it is product, it's multiplication sign between any two numbers. Okay? So we could also write this as 2 times 3 squared. That is the exponent form, right? Index form. So 2 times 3 squared is the shorter way of writing 18 with all its prime factors. So 18 has these three prime factors, 2, 3, and 3. Correct? So that is how we could do it. Perfect. So these are unique. So earlier, for example, for 12, we could say 4 or 3, 2 or 6. They are different numbers. But in this case, if you write them as prime factors, they're always unique, and that is important to note. So the composite number can be written as a product of prime numbers in exactly one way, and this is critical. And based on this, we'll have many questions to come. But to begin with, the question here is to practice. So the question is, write the following numbers as the product of prime factors. So we have three numbers for you. Take your time to write the prime factors of these, correct? In the form shown here. Is that clear to you? So that becomes your exercise. Now, let's take them one by one. So I'll actually take an example with a bigger number. That will help you, right? So we'll understand the method of prime factorization. It really means how do we write a composite number as product of prime numbers, right? So express 360 as product of prime numbers in index form, right? Okay, so we have two methods here. One method is called repeated division. The other one is the factor tree. So let's try to understand both these methods. So begin with the number which you want to prime factorize. Now 360 can be divided by which prime number? Think like this. It's an even number. Divide by 2. Half of 360 is 180. It can be halved as 30, 90. And then again divide by 2. You get 45. 45 can be divided by 3 or 5. Let's do 3 first. So if you divide by 3, you get 15 times is 45. Again, 3 times 5 is 15. So you land up with only the prime numbers. Do you see that? So we did all this repeated division to get the numbers which are 2, 2, 2, 3, 3, 5. So these are the numbers 2, 2, 2, 3, 3, 5. When you multiply them, you get 360. Why don't you check it out, right? Let's check it out. 2 times 2 is 4, 4 times 2 is 8, 8 times 3, oh well, we can do 3 times 3, 9 and 8, 72. And then when you multiply by 5, 72 times 5 is 360. Correct? Okay. In shorter form, we can write 2 cube, 3 square and 5. Since there are 3 2's, so it becomes 2 cube. 2 3's, 3 square and 1 5. So that becomes your form. So 360 is prime factorized. So that is one method. Repeatedly divide by the prime numbers. The other factor is factor tree, which could lead us to the same answer in a different way. So 360, as you know, you can divide it by any two numbers which are its factors. For example, 36 and 10. 36 and 10 gives you 360. Now 36 is 4 times 9, 10 is 5 times 2. Well, those are prime numbers. You cannot go further. But 4 and 9 are composite numbers. You can always divide them by prime numbers, 2 and 3 gives you 9. So what are you landing up with? You land up with, at the end of your factor tree, the prime numbers which cannot be further divided by any other number, since prime numbers have only two factors, 1 and the number itself. And there's no point writing 1, correct? So that is another method. So I hope this method is absolutely clear. You're there with me, correct? Fine. So you know how to do prime factorization. The unique thing about it is the set of factors which we get are all prime and they are all fixed. We know always you get the same factors. We did it in two different ways and we got the same set of numbers. Correct. Now we'll see how do we use all the information which we have learned to find LCM and GCF. We are now exploring into a new area, which is looking into the Venn diagrams. So, are you familiar with Venn diagrams? If not, don't worry much. We'll learn today and then see how Venn diagrams can help us with already gained knowledge and give us something more. Correct? Okay. So, the question now is find GCM and LCM, GC greatest common factor. Let me write down and LCM of 12 and 18. Okay, so let's do prime factorization of 12 and 18 to help us out. This is what we are going to do. So whenever you want to do GCM and LCM, you could factor, right? But prime factorization gives you a unique set. So prime factorization is important. So you could do prime factorization in two different ways. Let us do with factor tree also. So 12 could be written as 2 times 6, which is 6 could be written as 2 times 3, and therefore I could write 12 as 2 times 2 times 3. Do you see that? Okay. How about 18? 18 can be written as 2 times 9. We did it earlier. And then 3 times 3. So 18 can be written as 2 times 3 times 3. The other method was division, ladder division, which is shown here, right? So you're dividing by these numbers repeatedly and you get all the prime numbers at the end. And therefore, we can write down the prime factorization of the number. And now the question is, how do we find the LCM and the GCF? From here, it is clear that GCF is the common factors, right? Greatest common factor. So now let's again look at this. If you look at 12 and 18, 2 is common, correct? And then 3 is common. 3 is also common. So we have these two common factors for each. So when you multiply them, you get the greatest common factor, which is 6. Is that clear to you? Now let's look into the same process using the Venn diagram. How can Venn diagram help us find both LCM and GCF? Well, with factoring, you could find the GCF, but not the LCM. So let's see. We have the prime factorization, which is 2, 2, 3, in which we found that 2 and 3 is common factor. So when you make two circles, one circle is for the factors of 12, the other circle is the factor of 18, right? So whatever is common is placed right in the middle where they intersect. So 2 and 3 are the numbers which are factors of both 12 and 18. Now, what are we left with? We are left with the number 2 in 12. We have put it here. And we are left with number 3 in 18. We put it on the other circle as shown. So definitely what we have here is a greatest common factor, which is the product of 2 and 3, which is from the intersection of the two circles. How do we get the LCM? Can you tell me from this Venn diagram? Yes, you're right. So to get the LCM, we have to multiply all these numbers. So when you multiply all these numbers, 2 times 2 times 3 times 3, you get your LCM. Well, easy was. We have already done this part, correct? Which is the greatest common factor for us. Multiply by 2 and 3, the other one, and you get the LCM of 36, correct? So that is how we get it. So LCM was the product of all the numbers here, which was 2 times 2 times 3 times 3, and that gives you 4 times 9 as 36. Do you see that? What else did we learn here? Well, both LCM and GCF are related. So the common numbers are here. Now explore. Very important thing to explore here is that what is product of LCM and GCF? So you figure this out. So if I multiply 6 with 36, what do I get? And how is it related with 12 and 18? In a way, that is your question. You get it? So explore this and we'll move forward. Here is another example on the Venn diagram. I'd like you to pause the video, read the example, answer, and then move forward. Example here is to find the numbers from the GCF and LCM. So we are doing reverse calculation this time, right? So we are doing reverse calculation. So now we know what the GCF and LCM is. We want to figure out what the numbers are. Okay, so Venn diagram can help us. Let us see how. So the question here is, find two sets of numbers a and b whose greatest common factor is 8 and LCM is 48. So we are given that the greatest common factor is 8 and the LCM is 48. You have to find two numbers. How do we do it? Well, we learned that if we make a Venn diagram with two circles for number A and B, these are the numbers A and B, in that case, GCF is the common factor. So the common is 8. So in the intersection, we will write 8. Now LCM is what? LCM will be equal to, in this case, 8 times the numbers, let it be P and Q. We don't know what these numbers are. We need to find. So L times these numbers. But what we know here is that LCM is given to us as 48. So we can say 8 times something should be 48. You get the idea. 8 times something should be 48. So that is what we're looking for. So 8 times, what is this? So we know 8 times 6 is 48. That means the product of P and Q is equal to 6. So when you multiply P and Q, you should get 6. Oh, that means that the two numbers P and Q could be 1 and 6, 2 or 3. Oh yeah, that is how you're going to do it. Isn't that interesting? I hurriedly went through this solution for a reason. I want you to think about it, right? So think about it. And do you understand? Okay, I think you do. So let's go through these steps once again. So what we did is that we now understand that LCM is actually product of everything in this Venn diagram. Now everything here is the greatest common factor which is common to both, and whatever remains, which are, let us say, P and Q, something which we don't know. We know that LCM is 48 and GCF is 8. We'll replace these with 48 and 8. We're left with P and Q. Now, P and Q should be is definitely 6 because 8 times 6 is 48. So we are looking for P and Q as two numbers whose product is 6, right? 1 times 6 or 2 times 3. It could be 3 times 2 or 6 times 1. Well, any one of them. However, this is like same, right? P and Q. So we have two combinations, 1, 6 or 2, 3. So these numbers could be 1 and 6, or they could also be 2 or 3. Do you see that? Now, if it is 1 and 6, for example, then what is P? P will be 1 times 8, right? And Q will be 6 times 8, 48. You get the idea. So those are the numbers. So if I take 1 and 6 as the case, then what are the numbers A and B? Well, A will be 8 because it is, you can find P. You have to multiply with the common factor 8, right? To get all these numbers. Since the greatest common factor is 8, to this combination, we can multiply by 8 to get our numbers. So A could be 8 and then B will be 48. Multiplying 2 and 3 by 8 gives us 16 and 24. So these are the two sets of numbers which can lead us to our answer. You get the idea. Correct? Perfect? Okay. Now, from here you also see it is very interesting that the product of A and B is the product of LCM and GCF. We were looking into this question earlier. Now, is it clear to you how? Correct? Yes, it is. So you get the idea. How do we find the numbers from the given lowest common multiple and the greatest common factor? Very interesting, extremely important exercise which is not normally seen in the books. So that is what you learn when you are there with us. So here we'll note few more things, and that is product of two numbers is equal to product of LCM and GCF. So I'd like you to make a note of this. That will help us to solve such questions even faster, right? So, as we have seen, that there are many possible solutions for this. The numbers A and B could be 8 and 48, or they could be 16 and 24. Both these numbers will have the greatest common factor of 8 and the LCM of 48. Is that clear to you? I'd like you to verify the result, okay? Now here is the next example, and this time we're looking into three numbers, a Venn diagram with three numbers, and with that, we'll see how do we find LCM and GCF. Very efficient way of finding. So we're combining prime factorization, right? We're combining prime factorization and the skills for Venn diagram in this particular case. The question for us now is example 4. We need to find Gcf and Lcm of three numbers, right? And the three numbers given to us are 15, 24, and 30. First step first, we'll do prime factorization. So first 15 prime factorization is 3 times 5. Then for 24, keep on dividing by 2's. You're left with 3 at the end, and you get 24 as product of 3 times 2 times 2 times 2. For 30, keep on dividing as shown here, and the three factors, prime factors, are 3, 5, and 2. So we have this list, and from here we can see what is common. So when you look at it, we can see that the number which is common to all is 3, right? So 3 becomes the greatest common factor for this. Is that clear to you? Now let us see how do we use Venn diagram to find the LCM. Greatest common factor you could do otherwise also. So we make three circles, and this time the three circles are for the numbers given to us 15, 24, and 30. We'll begin with the center part, which is the greatest common factor. So in this case, we figure out that the greatest common factor is 3 for us, correct? Straight away from prime factorization. So we have substituted the number 3 here. How do you get 15 with 3? The other prime number which multiplies with 3 to get 15 is 5. You see that? So 5 gives you 15 with 3 as a common factor. So we get that number. How about 30? So we have 5 times 3 already in this blue circle. To make it 30, we will add the number 2, which when multiplied will give you 30. So the blue circle now has 3, 5, and 2. You get the idea. So we are now looking for 24. We have 3 and 2, 6. 6 times 4, but divide 4 into prime numbers of 2 and 2. So we get this 2 and 2, which becomes the factor for 24. You get the idea. So the gradually inside out is the strategy. So begin with the greatest common factor in the center, go outside and figure out all of the numbers. That is how you get the numbers from the given situation. So once you have all the numbers, the LCM is what? LCM is product of all this. Just multiply them together to get the result, which in this case was 120. Clear? So multiply all these numbers. 2 times 2 times 2 times 3 times 5 is the answer, right? So that is the way you could actually find the lowest common multiple. So we have used this strategy for prime factorization, Venn diagrams to get the result. Now here is another critical question for you. Here is the last example before we end our session, and this is kind of a extended example on prime factorization and how do we find LCM and GCF. So the question here is, prime factorization of numbers a and b is given below. So for number a, 2 cube times 3 square times 5 square, and b is 3 square times 3 cube times 5 times 11. Based on this, part A is find the numbers a and b, part B is find the GCF, and then C is find LCM. I'd like you to pause the video, answer this question, and then look into my suggestions. First thing first, how do we find the numbers a and b? We are given the prime factorization. That means just multiply them, right? So to find them, it is like you could do 2 times 2 times 2, and then we have 3 times 3, which is 9, and then we have 5 square, which is 25. You could do like this, or you could straight away write 2 cube is 8 for us, right? So we have 8, and then 3 square is 9 for us, and 25 square is 25. So multiply these numbers to get your answer. The second one here is the number b. So we have 2 square, which is 4, times 3 cube, which is 27, times 5 times 11 to get your number. So that is how you can do part A, which is how do we find the numbers A and B. Now, the second part here is to find the GCF. To find GCF, what can we do? Well, we can make two circles, the Venn diagram, right? So we'll use the strategy which we learned. The strategy here to discuss is whatever is common, we'll put them inside. So when you look at the twos, what happens? There are two twos in both. So 2 square is common. However, one of them is left for A. So for A, I have a 2 extra. Okay. Now let's look into the threes. 3 square and 3 cube. This time we have extra 3 on the B side. So 3 square is common and 3 is there for B. You see that? This index form really helps us to efficiently answer the question. As far as fives are concerned, fives, one of them is common, one is extra with 5, A, and with 11, it is with B. So we get all the numbers here. Do you see that? How easily we have found the answer. And clearly, from here, what is the GCF? Well, in this case, the GCF is equal to 2 square times 3 square times 5. Is that clear to you? And what is LCM? LCM will be the product of all others. So you just multiply the GCF with the remaining numbers, which in this case is 2 times 5 and 3 times 11. That is 10 times 33. And you get GCF and LCM. Do you see that? So that is how you can easily answer such a question. It's a very difficult question which takes a lot of time to answer, but with the techniques learned, see how efficiently we have answered this question. Here are the calculations for you, right? So let's review what we did. Well, the number A is 2 cube times 3 square times 5 square, correct? You could multiply them, and in multiplying also, it is interesting that I combine 2 square and 5 square. Since 2 times 5 is 10, that gives us 100. Do you see that? And this is 9, so 2 times 9 and 1800 is the product. So if you combine the numbers, the calculations may become easy. Since in many exams, especially the Olympiad, what we look into is questions should be solved without a calculator, right? Many exams will not let you use calculators, so there it helps. For B, again, we'll do the simple product and get our answer, which is 2970. So we know part A, which is how do we find the numbers themselves. And now we're looking into part B, which is how do we find the greatest common factor. So as I showed you, you begin with what are first two, right? So in twos, how many twos are common? One of them is common. The one which is not common, keep it outside. You see that? Now, similarly, go back to threes. So when you see threes, 3 square is common, and in that case, 1 is left, which comes to side B. So in this case, we have written the numbers A on the left side and B on the right side. Now, in that case, we have taken care of threes. Now, with fives, one of them is common, put them here. The other one goes with A, and 11 comes with B. So we do have a set of numbers here. Center numbers, when multiplied, will give you the answer, which is 90, right? We actually got something different. What happened? Oh, the numbers typing error, right? So here B was a different number. We had written 2 square, and that is why we got that answer correct. But it's okay. In this case, we have taken only 1, 2. So these are different numbers, right? So here, this difference, right? So it is with a difference. And the difference is a factor of 2 in B is missing in this case, right? But anyway, this could be a new question, right? So let's call it a new question. So don't compare with the previous one since the value of B is different. Okay, that's interesting. So sometimes the typing error leads to a new question. That's interesting. Okay, so we did get the GCF, which is 90 this time. To find the LCM, it is basically the product of all the numbers, including the GCF. Now, when you multiply these numbers, you may need calculator to do so. You get your answer, which is 59400. Is that clear to you? Perfect. So with that, we end our session of learning on this side, but we'll explore further with the help of some questions. So that brings us to the first question on what we learned just now. The question here is, prime factorization of a number n is 2 square times 3 cube times 5 square times 11. And the question 1 is, which of the following is not a factor of n? Can you tell me? Which of these are not a factor of 10? 100, 108, 144, 297. Take your time to answer this question. We already have 2 square, 3 cube, 5 square, and 11. Okay, so you have to try it out. 2 square means 4, and that will divide 100, right? How about 108? 108 is 4 times 3. That will give you all the factors, and this is like 12. 12 means 4 times 12, 12, right? 144 is 12, 12. Does it have 4 times 3? We don't have another 4, correct? So that may not be the case. So you need to like rationalize your thinking and then figure this out. 297, 297, 7 and 2 is 9, and we have 9 in between. So it will go with 11. So yes, that will go. So that is perfectly fine. So I think the answer 144 is not a factor of these. So that is very critical, but it's an interesting question. You should understand how do we find this answer in a different way. So I'd like you to explore and find a way to answer this question quickly. You get the idea. Well, 144 seems to be the number which will not have these factors, or I mean, which is not divisible by, which is not a factor of this. So this is clear. Which of the following is not a factor of n? 144 is not a factor of n. We can figure this out because we are working with 2's and 3's, right? That will not give us 144. Now, second question is, what is the value of n? Value of n will be multiply them all together and then match your answer. Is that clear to you? To multiply, this is a better technique. You could use 5's and 2's, which will give you 100, and then you can use 9 and 99. 99 is 100 minus 1, right? 99 is 100 minus 1, and that can help you to find a quicker answer. Perfect. So that is where we are, and we are going to end this session here. And in the next part, we're going to look into the divisibility rules, right? So let's end with the factorization. That becomes an extremely important exercise for you. I can actually give you an assignment based on this, whatever we have learned. And here are 3 questions for you for the assignment. So let me just, I'd like you to pause the video, copy these questions, and that becomes the assignment for you. You may submit the assignment online as an attachment to an email, and then we can discuss further. How do we answer these questions, correct? So I hope with this, you have learned a lot about prime numbers and how do these prime numbers help us in finding LCM and GCF, right? See the connection. So that is how we could do all this. I hope you find it interesting and useful. Take your time, review, and don't forget to submit your assignment. Thank you and all the best.